Let's see what happens when we burn some food. All right, so who here likes gummy bears? Yes, everyone loves gummy bears because they taste good and they give you lots and lots of energy. And they give you lots and lots of energy because they contain so much sugar and your body converts that sugar into energy. So today we're going to show you just how much energy there is in a single gummy bear. So Horst and Yakov are going to melt this salt that we have here. We have some salt in a test tube. All right, so this might take a little minute because salts have a pretty high boiling point. And while they're doing that, just a quick word of warning, you'll see that there's a lot of energy in a gummy bear, so there's going to be a bit of smoke, and sometimes the reaction can get a bit violent, which is why we have this shield here to protect us. All right, I might choose my victim. What colour should I use? Good call on the yellow. I think yellow's a good idea. There we go, we have a yellow gummy bear. All right, so it's starting to melt. You can see we've got a little lake of salt. Some solid stuff still in the middle. Just going to move over here. All right, nearly there. All right, let's find out. All right, so what you just saw was all of the sugar energy in a gummy bear being converted into light and heat and sound. So as you can see, there's a lot of energy there.
So we're going to keep going on this food theme, Mr. Minshew, but we're going to go back to ice. Now, I have here this is just a Milo tin. We all love Milo, don't we? I've just taken off the label. Now, what I'm going to do is take some liquid nitrogen. I'm going to put it in the tin. Now, what's going to happen if I put the lid back on the tin? It's going to explode? Well, there's only one way to find out. Okay, ready, set. Should we do that one more time? How's that? So, this tin's kind of cold right now. So what we saw there was how that pressure built up. Now, typically what we do, except that one works so well, I decided not to go on with it, is we use tins of different sizes. Now, generally, at least most males will go, oh, bigger tin, that'll go higher. Not always. What we're dealing with here is pressure. Now, pressure, the equation for it is force per unit area. So if you have a bigger tin, you can get a bigger force, but it's going to be spread over a bigger area. So it all depends on how well you can actually grip. And that lid actually gripped incredibly well. So it's always important to remember that a greater force doesn't always produce the best result. And that actually comes in a lot of things, especially with pneumatics and that type of stuff. You can use quite a small force to move quite a large object. Anyway, back over to you guys.
Who of you wants to see a bigger bang? Who of you thinks we chemists can make a bigger bang than the physicists? Who of you thinks we can make a bang with flames? Okay, remember the balloons at the beginning? Do you know what was in them? I heard the right thing, hydrogen. In the first show we had a couple of people that were saying helium. It's not helium, because helium is what you get in the card shop for Valentine's Day. If what was in the balloons, if that had been helium, then you would bring your loved ones a bomb for Valentine's Day. Not exactly what you want. So hydrogen, one of the most flammable gases on Earth. So what we're going to do is, we've got a nice coffee tin. Even smells like coffee. And we're going to fill it with hydrogen gas. Completely and fully. Until there's only hydrogen left in there and no air anymore. So while I'm doing that, Jakov is already lighting the candle, because we obviously need a flame if you want to have a bang with a flame. Okay, that tin is now full. And if I carry that tin over here, then Jakov is already ready. And as you can see, he has a very, very long stick. And he knows exactly why. And Karsten is already kind of cowering there. And she knows also why, because this is going to be loud. So if I rip this off, then we get a blue flame burning. And that blue flame sucks hydrogen out of the tin and air steams in, until at some point we've got enough air in the tin for the tin to go... roast coffee.
So I have a question for you all. Who here knows what this is? That's right, it's a rocket. So this is most rockets, like the things that sent man to the moon and whatnot, are powered by hydrogen. So that's exactly what we saw made the tin pop there. This rocket is slightly different because we're going to power it using liquid nitrogen. So, first up, I showed you how much it could expand. Gases expand when they heat up. In the case of liquid nitrogen, when we go from a liquid state to a gas state, the volume increases by about just under a factor of 1,000. So if we were to have 1 cup of liquid nitrogen and let that boil off, it'd create a volume the size of a bathtub. That seems a bit weird, filling an entire bathtub with just 1 cup. So we're going to take advantage of this. So we're putting in our fuel. All right. Good to go, Chris?
We're ready.
Okay, here we go. 3, 2, 1. So as you can see, you only need a little bit of fuel to send the rocket quite a long way.
We've got a little bit of a fire and ice theme going on here. So this time we had a rocket propelled by ice. So what are we going to have now? Fire. And what does rocket and fire tell you? Where do we use rockets apart if we're from NASA and we want to fly to the moon? Fireworks. Every time you watch fireworks on New Year's Eve of a river fire, we've got rockets shooting up in the sky. And what do those rockets do apart from explode? What is the most noticeable thing about fireworks? Colors, yes. Each of the fireworks has completely different colors, and that's what we're trying to recreate here for you. Now, try as we might, UQ Security, funnily enough, had a couple of objections against us letting a couple of rockets loose here in the lecture theater. I really can't think why. So what we're going to do instead is we just show you the different colors that we get in fireworks. So what we got here is just a little bit of alcohol, which normally burns colorless, and then some salts. And those salts give the flames completely different colors. So what we got here on the left, burning in green, is copper. Then next, in this light red, we've got strontium. In this pinkish red, we've got lithium. Then we've got potassium, which should be pink, but is a little bit hard to see. Then we've got sodium in this bright yellow. That's the sodium that you know from the sodium lamps from normal street lamps. Then we've got boron, which is slightly green coming up there through the orange. Then we've got barium in that pale green. And finally, calcium coming up in this really nice orange. So all the colors of the fireworks. And those things aren't just looking pretty. These things actually sparked one of the largest revolutions in the history of science. Because people knew about those colors, they started asking questions along the lines of, why do the flames have all those different colors, from green over pink to yellow and orange? And when they started thinking about it and looking into it, then that developed the field of spectroscopy, and which in turn then led to quantum mechanics. Quantum mechanics is one of the most fundamental theories that we have about the world around us today next to general relativity. So from really pretty colors, you can get deep down to the most fundamental things of science. And now I just have to get rid of all those flames before they burn too much.
So it's nice for those chemists to show us how we can generate flames in the different colours. Now with a bit of physics, I'm going to show you what you can do with flames. So what I've got here is actually some of the salts. If memory serves me correct, this is some lithium. That was the red colour we saw before. So I'm just trying to, hopefully that's going to dissolve a bit. And I'm using a bit of my secret mystery ingredient X. So I'm going to light this up. Now I'm just going to put this little column cage over the top. All this is designed to do is to help separate the air near the flame from the air in the room. For instance, if you were to take a teaspoon and a cup of tea, stir it, you're going to get a little whirlpool. If you do that in the ocean, you're not going to see anything because the ocean's just too big. So that's why I'm just trying to separate it. So what I'm going to do then is slowly spin this. So there's a little bit of different, couple of different effects happening here. The first is just with the column spinning, it's acting like a centrifuge. So the heavier elements, the heavier air above it, the cold air, gets pushed to the outside, and the hot air gets to stay and remain in the middle. Now that the hot air doesn't have cold air on top of it, it can move up quicker, so the flame can get higher. Secondly, when this hot air moves up, it's at a lower pressure than the still air around. So that helps suck more air up the bottom where the source of the flame is, so it gives it more oxygen, so it can also burn brighter.